Good morning, everyone. Today we will continue to talk about the chapter 16, superposition and standing waves. And uh, like today we will finish chapter 16, and tomorrow we will have the exam one. And the exam one will cover chapter 14 to 16. So uh, I think you need to review all the homeworks, for the chapter 14 to 16. And I will the all the questions, all the exam questions is based on the homework questions. Like maybe just a change some value or data, but the similar questions like that. So please review all the homework questions. If you have any question, just let me know. Okay, let's talk about let's have today's class. Let me share my screen. Mm, wait me for a moment. Let me share my screen and okay. Let's start today's class. Today we will continue to talk about the superposition and standing waves. And uh, like we know next class we talk about chapter 16's goal. The goal for this chapter. We try to use the idea of superposition to understand the phenomenon of interference and standing waves. You can see, I think many students have this experience, and you just hold tab, long tab, and then you speak using this tab, and you can see your voice like uh, is stronger. Yeah, because there are some there have some superposition phenomenon and generate the standing waves. Yeah, does it make sense to you? Okay, yeah, after we have already talked about something on in next class, I think you will you will know uh, how this situation happen and why the sound is is more powerful than the usual you speak. Yeah, does it make sense to you? Okay, like today we will this is our today's goal. And firstly, we will review superposition and standing wave. What is superposition? What is standing wave? And what's the most important thing in that class? And then we learn about speech and hearing, and how superposition and standing wave help us to speak and hear, and how our how can we hear different sounds and speak different in different tone like that. Okay, after that we understand the interference of waves from two sources. Yeah, if there are two sources, like two different sound source or two different light source or any other wave source, and understand the interference, yeah, of waves from two sources. And then there is one application. Let's try to explore the beats. Yeah, I think you are familiar with beats, but how can the beats come out, and why the beats is just like that? Yeah, we will talk about that. Okay, let's continue today's class. Firstly, let's review the content we have learned in last class. Let's try to recall the principle of superposition. Yeah, when two or more waves are simultaneously represent at a single point in space, like the displacement of the medium at that point is the sum of the displacements due to each individual wave. Yeah, this is we call it superposition. You can see for a real thing, like for a ball, and for the things we see in the real world, it cannot be in one location. at the same time. Doesn't make sense to you? But for the wave, no matter it is a stream wave, water wave, light wave, sound wave, yeah, actually, two or more waves, it can be spontaneously present at a single point in space. Yeah, we call this like a phenomenal superposition. And the displacement of the median at this point is the sum of the displacements due to each individual wave. Yeah, we have a talk about in next class. And then we talk about the standing wave modes. And actually, the superposition can generate standing waves. And you can see if there like a the wave like just go go forward and back, and also there it will oscillate, like the standing wave is just it oscillate up and down. They will now travel, yeah. And for different situation, for different, yeah, for different, oh sorry, yeah, there are different situation wave. Let me try to, so sorry. Mm. Yeah, you can see for the wave on the string, and for the sound wave in open tab, and the sound wave in closed tab, they have this share the same pattern for the standing wave. And you can calculate the wavelength using this equation. This is the string length or the tab length, and this is like a mass no, for string, or mass for the monocular. And this is the frequency. Yeah, this frequency, and based on this equation, because frequency is equal what? Equal V divide lambda m, right? So then you just put a lambda m here, and then you can get this equation. Yeah, and for this three situation, wave on a string with fixed ends, and a sound wave in open tab, and sound wave in closed tab, and you can calculate the frequency using this equation. And the m is just like the how many antinodes, yeah, here. Yeah, the mode number m can be any positive integral, because you can see if you want this one is the antinode, this one is the antinode, and then the m you can be any positive integer. But for the sound wave in open closed tab, you just you use this equation, because this kind of situation, the frequency will be half this equation. Yeah, we talk about y. Yeah, because you can see for this equation, it should be one end is like a antinode, one is like a node. So it should, for the m, it should not be from any positive integer. It should be like the odd number, odd number. Otherwise, this situation will not happen for one antinode and one antinode and one nodes. Yeah, we have already talked about this, and we talk about y is just half the this situation. Yeah, you can review what we have already talked about in last class, and any question, just let me know. Okay, like here, sorry, here, in this section, and firstly we will talk about speech and hearing. And at the beginning, let's talk about the frequency spectrum. Yeah, most sounds are a mix or superposition of different frequencies. Yeah, actually, most sounds is just not a single frequency, single frequency signal. Yeah, it's just a mix or a superposition of different frequency. And the frequencies spectrum of a sound is a bar chart showing the relative intensities of different frequency. Yeah, for example, here is one sound. Yeah, this is sorry, what's this? Yeah, here is one the frequency spectrum for one sound, and you can see like for this sound, like it includes different frequency. Like this peak is the fundamental frequency, and these peaks are the higher harmonics. And yeah, your brain interprets the fundamental frequency as the pitch and uses higher harmonics to determine the tone quality or timbre. Yeah, which means this from fundamental frequency is just decided, it's just determines the pitch. And the higher harmonics, those are the higher harmonics. You can see it is from this one to this one. It is uh 262. Does it make sense to you? And this to this one is also 262, and this one to this one is 262. Yeah, here it's just like this peak these peaks like this frequency peaks is just like a has a fixed period, and those we call this the hair harmonics, and the harmonics can determine the tone quality like this like a hair harmonics what's the period between different frequency like which decide what's this sound like a look sounds what's this sound looks like it is from a piano or it is from a flute or it's from a human body like that. So like this hair harmonics determines the tone quality, or we can call it like a timbre. Yeah. Yeah. Does it make sense to you? Okay. And the tone quality is what makes a note on the trumpet sound differently from the same note. Yeah, like a frequency played on a guitar. Like I said, the tone quality is what makes a note on a trumpet sound differently from the same note played on the guitar. The frequency spectrum is different. You can see here. Even like the fundamental frequency is the same like maybe same frequency and but you can see if the period is a harmonic the hair harmonics is different and which represent different like different two quality and which decide this sound is from the trumpet or is from a guitar or from a piano. Yeah, like this two qualities which means the harmonics the hair harmonics like decide the tone quality decide this sound from which like a source like that. It doesn't make sense to you. Okay, the hair harmonics don't change the period of sound wave. They change only its shape. You can see here. The sound wave is usually periodic. The vertical axis is change in pressure from the atmosphere pressure due to the sound wave. Yeah, usually the hair harmonics don't change the period of the sound wave. Yeah, the hair harmonics usually has a fixed period. You can see here. Uh, yeah, it has a fixed period like it has a fixed period, but it changes only its shapes. You can see here in this frequency it is just this low. In this frequency it is this low, and maybe in this frequency different different maybe different instruments maybe has a different shape. Yeah, also or like maybe they have different like period. Does it make sense to you? Okay, yeah, and let's talk about this is like the frequency spectrum like every sound every sound can be presented by a like frequency spectrum. Yeah, this is just a one kind of like a sound, and you can use the like a fundamental frequency and the higher harmonics to and the relative intensity to represent this sound. Yeah. Sorry. Okay. Uh, okay. Let's continue. Yeah. Then we talk about the valves and formants. Yeah, speech usually like a speech begins with the vibration of vocal cords stretched tissue in your throat. Yeah, I think we know that. Am I right? Usually, if we speak, like it just like come from the vibration of vocal cords and stretch tissue in your throat. Yeah, and your vocal cords produce a mix of different frequencies as they vibrate. The fundamental frequency and a mix of harmonics. Yeah, you can see this is like a vocal our some person's like a sound, and you can see here is some like a fundamental like a frequency, and then there are different period for and this is we call it hair harmonics and our like vocal cords like produce this mix of different frequency as our like vocal cords vibrate. Yeah, this is the fundamental frequency and the mixture of hair harmonics. Yeah, this like these things is just the representation of our vocal cords. That makes sense to you? Yeah, this creates the pitch of your voice and can be changed by changing the tension in your vocal cords. Yeah, you can see some like when you want to change your like voice, maybe you just like change the like your vocal cords like the shape like the or you can see if you change your like mouth shape like your voice will change. Doesn't make sense to you because your vocal cords like the tension of your vocal cords change. Yeah, any questions just let me know, okay? And you can see sound then after you like like quick like your voice after you make some like a voice and this sound some sound and then pass through your vocal tra tra tract. Yeah, a series of cavities. Sorry. Yeah. Serous nerve cavities include the throat, mouth, and the nose that act like tubes. Yeah. And the standing waves resonances in the vocal parts are called formants. Yeah, you can see like the sound like through goes through your throat, your mouth, and your nose. Yeah, those kind of things are just like tubes, and these tubes can like generate the standing waves. Yeah, the standing wave resonates in the vocal tracts. We call it ferments. And you change if you like I said, if you change the shape and the frequency of the formats, and thus the sounds you make by changing your mouth opening and the shape and the position of your tongue, yeah, will make your voice change. You can try that, yeah. Try to like change your mouth opening or the shape of the shape and the position of your tongue, or yeah, you can change your voice. Yeah, that makes sense to you. Yeah, you can see here like this like a frequency spectrum is actually spoken frequencies. Yeah, and when you form your vertical tract to make a certain voice sound, it increases the amplitude of certain frequency and suppress others. Yeah, you can see when you like make a certain well, yeah, and the broad peaks at which amplification occurs are due to filtering by the formats. Yeah, you can see here because the standing waves resonance will like strength some specific like a frequency. And firstly, this is the first format, and you can see usually like the ideally, and the frequency like spectrum just like this for the and it will like from high to low. But in the real thing, and yeah, you just try to and because the throat, mouth, and nose and it can generate some like resonance like phenomenon, and it will like make some frequency like bigger, yeah, and like make some frequency like smaller, yeah, and then like this kind of like is our actual spoken frequencies. Does it make sense to you? Yeah. Okay, let's continue. And yeah, this is what we talk about, like speaking and hearing. Like this is for the like how a sound, what a sound looks, what a sound, how a sound looks represented by a mathematics form like that. Yeah, and how to make change to our which one is related to which like kind of which types of sound like properties and features like that, and how to change those features to change the sound. Yeah, does it make sense to you? Okay. Let's talk about the other thing, like the interference of waves from two sources. You can see here, yeah, there are two loudspeaker. Yeah, there are two loudspeaker speaker are spaced exactly one wavelength. Here is one wavelength. You can see here, here to here is one wavelength, and apart. Assuming the sound waves are identical, yeah, like this speaker and this speaker, they generate the same like sound wave, and the wave will travel on top of each other, yeah, like on, travel on top of each other because they just like in a line, and one is behind the other one. Yeah, superposition says that for every point along the line, yeah, for every point along this line, the night sound pressure will be the sum of the pressures. Yeah, the net sound pressure will be sum of, yeah, you can see these two will be, because the loudspeakers are spaced one wavelength apart. The crests and thrones are aligned and therefore are in phase. Yeah, because you can see they just like one wavelength apart. So the like a wavelength, the wave, the sound wave will be the same. Like if the crest, it will like surrounds, it will surrounds. It doesn't make sense to you. And waves, like we call this situation are in phase. Like those two like sound wave are in phase. Like waves that are in phase will have constructive interference. Yeah, like those the superposition is a traveling wave with like a wavelength lambda. Yeah, because this is a like a to seem like a sound wave, and twice amplitude because those is the amplitude is those two like plus together, so it is so yeah, so it is like the superposition is like a traveling wave, like this with this wavelength lambda and twice amplitude. Does it make sense to you? Yeah, because you can see here, this is the superposition. The like amplitude will be like twice this one, and the like wavelength is just like the sorry here, it's just like the lambda. Yeah, it's just the wavelength like as the original one. Does it make sense to you? Okay. Based on what we have already learned, like the superposition thing. Yeah. Okay. Let's continue to talk about the interference along a line. You can see if the D1, D1 is the like the distance, like the from the loudspeaker. Here is the loudspeaker to the observer. And the D2 is the other loudspeaker, the loudspeaker two, like the distance between loudspeaker two and the observer. And this distance, we call it like the path length difference, like those difference, like for those two like distance, the difference of those two difference, we call it path length difference. Two waves will be in phase and will produce constructive interference. Yeah, we have already talked about it. And in time, their path length difference is a whole number of wavelengths. Yeah, this is just like some result, some like observe the result we have already get like two waves here. Two will if it is in phase, and it will like produce constructive interference anytime, like when their path length, which means this difference like is a whole number of wavelengths. For example, like a wavelength is lambda, and which means the path length, this delta D should equal what? Lambda or 2 lambda, 3 lambda, just the whole number of wavelengths. Does it make sense to you? If this difference, the path length difference is this one, and which means those two waves produce like will be in phase and will produce constructive interference. That makes sense to you? Yeah. Okay. And when the speaker are separated by half of wavelengths here, the distance, like the path length distance, yeah, path length difference. Sorry, will if it is half a wavelength, like a 0.5 lambda, the wave we are alternate phase. Yeah, because you can see alternate phase. Yeah, the sum of two waves is zero at every point. This is destructive inference. Yeah, in this situation, if the difference path length difference is half wavelength, and then those two waves are out of phase, and the sum of two waves is just zero at every point. This is destructive inference. Yeah, and I think this is easy to understand. We have already talked about some in last class. And the two wavelengths will be out of phase and will produce destructive inference if their path length, this distance is a whole number of wavelengths plus half of wavelengths. Yeah, for example, here, if it is 2 over lambda, am I right? If it is lambda plus half lambda, if it is 2 lambda plus half lambda, or 3 lambda plus half lambda, which if the path length difference is in this situation, and then the two wavelengths will be out of phase and will produce destructive inference. Does it make sense to you? Yeah. Okay, this is like the two different like interference. Yeah. Okay, like for two identical sources, the waves, constructive interference occurs when the path length difference is this one. Yeah, we have talked about this. Is just summarize what we have already talked about. If two, yeah, only if only the path length difference equal equal like a number yeah, number like a whole number multiple like the wavelengths. Yeah, does it make sense to you? And the destructive like interference occurs when the path length difference is like a it's just like a one like a the wavelengths plus lambda, the number wavelengths plus the half lambda. Yeah, it's just equal lambda plus half lambda. Doesn't make sense to you. We have already talked about this. Yeah, this is a summarize. Okay, let's talk about some questions, quick check questions. Here, there are two speakers are emitting identical sound waves with a wavelength of 4.0 meter. And the speakers are 8.0 meter apart and directed toward each other as in the following diagram. Yeah, this diagram here. And at each of the noted points in the previous diagram, the interference is constructive or destructive or something in between. Actually, yes, those one is a little tricky. Yeah, we have already talked. Sorry, we have already. Yeah, we have already talked about the like how to tell like the construct if it is constructive interference or this like this adjunctive interference. But the thing is, for two identical source of waves, yeah. So, but for this question, yeah, you can see here those those like uh, those speaker will generate uh, like a sound wave. Actually, those will generate the same like identical sound wave, but in different position, different direction, which means it will also generate this one here, 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 here. You can see it is just opposite with this one. Yeah, so it because the position, those two are not like a direction to have the same direction, like not face to the same direction. It's just a face to the opposite direction. So which means it generates the identical sound waves, but it's because of the direction is opposite. So those two like sound waves are just like the outward phase. Yeah, does it make sense to you? So if you like know this thing clearly, so I think the answer will be easy to you. It is destructive. Yeah, destructive. Doesn't make sense to you. Yeah, because like even if they uh, emits the identical sound wave, but the phase direction is totally opposite. So which means they are alternate phase. Yeah, does it make sense to you? So the question will be B. All points are destructive. Does it make sense to you? Okay, let's talk about the other one. You can see two here. Yeah. Yeah, two loudspeakers emit sound waves with the same wavelength and the same amplitude. Yeah, those two. Yeah, the waves are showing displaced for clarity, but assume that both are traveling along the same axis. At the point where the dot is, at the point where the dot is, it is the sorry. So if interference is constructive or destructive or somewhere between constructive and destructive, or not enough information to tell about the interference. Yeah, actually you can see here there are two loudspeaker, but with the same like wavelength and the same amplitude, and yeah, and assume that both are traveling along the same axis. Yeah, because is here is just for you can see it clear, but it should be like a overlap. This one should here. Am I right? Like yeah, this is two. So which means here the distance, the delta d should be one meter. Am I right? And here the lambda equal what? They have given you the lambda. The wavelength is 2. Am I right? So the delta d equal what? Half lambda. Am I right? So which one is right? Yeah. When the like path length distance a difference is half lambda, it should be the interference. It should be destructive. Does it make sense to you? Yeah. We have already talked about this one. Yeah, this is the right answer. Yeah. Any question? Okay. Yeah, because the delta d here is delta d equal half lambda. Yeah. Okay. Let's check the other one. Yeah, this is a similar thing. The two loudspeakers emit sound waves with the same wavelength and the same amplitude. Which of the following would cause there to be destructive interference at the point of the dot? Here, yeah, you can see. For now, you can see. We need to pay attention to the difference between this one and this one. You can see the delta D is the same thing. Am I right? 1 meter, but the lambda changed it from 2 to 1, which means for now the path length difference is just equal lambda, which means it like those two just has like a constructive interference. Yeah, but if you want those two have a destructive interference, which means you just change the path length difference, and those like move speaker to forward one meter, which means it will become this bit become 2. Am I right? And it is 2 lambda. Yeah, it's not like it will also have the constructive interference based on what we have already talked about. And the move speaker to forward right 0.5 meter, which means the delta D equal what? 1.5. Am I right? 1.5, which is like a 2 lambda plus half lambda. Am I right? Sorry, which is lambda plus half lambda. Yeah. So this one is right. I'm right because this path length difference is one like a number multiple like lambda and plus half lambda. Yeah, that makes sense to you. Okay, this one is right. And move speaker 2 like backward 0.5 meter, like which means the D. Let me see. Let me see. The D will equal what? Mm, will equal 0.5 because it will move to left, which means here the delta D equal what? Half lambda. Am I right? So which means this if they move the speaker 2 backward left 0.5 meter, which means it will would cause these two like be disrupt conjunctive interference. Does it make sense to you? Yeah, and if like let's check D. Move speaker 2 backward 1 meter, which means 1 and 2 will overlap, totally overlap, which will not have the destructive interference. Obvious, it will have the constructive interference. Does it make sense to you? Okay, which means yeah, you can see like the E obvious is not right because we have already found that BC is right. So the right answer is B and C. That makes sense to you? Okay, yeah, this is the right answer. And let's explore one example, like interference of sound from two speakers. Yeah, like let's talk about this example. Susan stands directly in front of two speakers that are in line with each other. Yeah, actually, like those two speakers that are in line with each other. The farther speaker is 6.0 meter from here. Like the farther, this one is farther one. It is 6. I'm right. And the closer speaker is 5 meter. I'm right. Yeah, which means the delta D equal what? Delta D equal 6 minus 5 equal 1 meter. Does it make sense to you? Yeah, and the speakers are connected to the same 680 hertz sound source. Yeah, those two speakers yeah have the same like frequency sound wave. And so then here's the sound loud. Here's the sound loud and clear. The frequency of source is slowly increased until at some point Susan can no longer hear it. What is the frequency? When this cancellation occurs, assume that the speed of the sound in air is 340 meter per second. Yeah, let's talk about that. Like you can see, Susan hears the sound loud and clear at the initial frequency of 680 hertz, which indicates constructive interference with delta D equal m multiple initial wavelengths. From the information given, we can find the delta D and lambda like wavelengths initially. And thus m, yeah, and then we can find m. This destructive interference will occur when the frequency is increased, and the wavelength will decrease because like we know the lambda equal what? Lambda equal v divided f. Yeah, if the frequency is increased, the wavelength will like decrease. Yeah, until like if the delta d, I think it is delta d. Sorry, equal m plus half lambda final. Yeah, this is what we need to we know for this equation. We know that, and this will determine the final wavelength lambda final, and hence the final frequency. Yeah, does it make sense to you? This is what we analyze these questions, and you can see we, like we will start with a visual overview of the situation as shown in this figure. Sound waves from the two speakers overlap at the Susan's position. And the path length difference, yeah, actually we have already talked about that. The actual distance traveled by the wave from speaker one is just the distance difference in the distance from the speaker to Susan's position. In this case, the delta D is 1 meter. Yeah, we have this is 5, this is 2, and this is delta D. Does it make sense to you? And initially, with a 680 hertz tone and a 340 meter per second sound wave. Then the wavelength, yeah, we know this lambda equal V divided F. We know the V, we know the F. Then we know the initial like wavelength is just this one divided this one. It's half meter. Am I right? Like a 0.5 meter. You can see the distance is 1 meter, and the initial is half, and delta, which means delta L equal to lambda initial, which means it's a constructive like interference that will happen. Am I right? At the beginning, so the Susan hear the clear and loud sound, and then here we want to like find the value of m from like for now what is m? Yeah, we just use the delta m d divide lambda initial equal to, which means lambda d equal to initial wavelength. We say that the m is a whole number as expected for constructive interference. As the frequency increases and the wavelength decreases, at some point the like a criterion for destructive interference lambda d should equal this one. Like here m equal, because m equal what? 2. So and the difference d should equal 2.5 final wavelength. Then like this like two wave sound wave will have the destructive interference. Does it make sense to you? So then we from this equation here, don't forget this delta lambda final will equal delta d divide m plus 0.5, like divide 2.5, which is 1 divide 2.5. It is 0.4 meter. Yeah, yeah, we know lambda final, and we know v like velocity of sound wave. So then we can find the corresponding frequency. Does it make sense to you? Yeah, like the corresponding frequency will like v over lambda. Yeah, it's 850 50 hertz. Let's access this like solution. 850 hertz is an increase of 170 hertz from the original 680 hertz, an increase of 1/4 of original frequency. This makes sense. Original 2 seconds of the wave fit in the 1 meter path length difference. Now 2.5 cycle fit, an increase of 4/4 of the original. Does make sense to you? Yeah. So yeah, if you meet these equations and you just remember those kind of equations, yeah, those two equations for the constructive, like the path length difference should equal this one, and the destructive interference for the destructive interference, the path length difference should be equal this one. And then yeah, some basic equation you also need to be used. For example, lambda equal v divided f, or f equal v divided lambda. Yeah, just try to remember these equations and know yeah, those are some basic equations. Okay, let's continue to talk about the interference along a line. Yeah. And if two loudspeakers are side by side, yeah, side by side is drawn is now in a line, and one emits the exact inverse of the other speaker's wave. You can see this wave emit this one, and this means it's just like if like a exact inverse of the other speaker's wave, then there will be destructive interference and the sound will completely cancel. Yeah, even they are now in the same line, they just side by side for the and those two waves will be like destructive interference and the sound will completely cancel. Yeah, you can see, for example, the headphones with active noise reduction mirror the ambient sound and produce an inverted version to add to it, lowering the overall intensity of the sound. Actually, if you have the headphones with active noise reduction, which means those headphones or earbuds mirror the sound from the environment and then produce an inverted version like a sound wave to add it and lower the overall intensity of the sound. Doesn't make sense to you? It just use this disconjunctive interference to reduce the noise from the environment, the outside environment. Yeah, does it make sense to you? Okay. Let's let's try to talk about interference of spherical waves. Actually, we talk about we just talk about the interference of along a line. Yeah, but usually in practice, the sound waves from a speaker or light waves emitted from a light bulb spread out as spherical waves. They are not like the line stream waves. Yeah, like that. It's just like emitted from emitted as spherical waves. Like the wave fronts represent crests. Yeah, this is front represents crests, and halfway between two waves fronts is throne of the wave. This is crest. This is a throne. This is a crest. This is crest. This is throne. Yeah, does it make sense to you? Uh, so yeah, throne of the waves. Yeah, this is just some definition. Yeah, and some practical situation. Yeah, and yeah. Also, this those spherical waves have the interference situation phenomenon. The interference occurs where the waves overlap. You can see those two. There are two different speakers. The red dot here is the red dot, and presents a point where two wave crests overlap. You can see this is the crest. I'm right. This is circle is a crest. So this is through one speaker one's crest and also speaker two's crest. Does that make sense to you? Yeah, the black dot here it cross it like it is at a point where a crest overlaps. Here is a crest, but here is just for the speak two, it is so the wave interference is destructive. Yeah, does it make sense to you? Yeah, one is a crest and the other is a thorn. Here, wave one is a crest, the other is a thorn. Yeah, does it make sense to you? Yeah. I think I just. Yeah, here is more. Yeah, and then for the dot, black dot, like the wave interference is destructive. And counting the wave fronts, we see that the red dot is three wavelengths. Let me try to make it clear. Yeah. Okay. Yeah, this red dot Yeah, for the speaker one. And for the speaker two, here, speaker two is let, this first two, 1, 2, 3. Yeah, it is like a three waves from like speaker two, and like for the speaker one, it's 1, 2, is two wavelengths from speaker one. So the path length difference is R2. Here is here is R2. Sorry. Yeah, here is R2, and here is R1, which means that the like path length difference is R2, like R2 minus R1 equal 1 lambda, because R2 equal like 3 lambda, and R1 equal 2 lambda, which means the difference is 1 lambda. The path length difference of the back dot is, you can see here. Let me, yeah. Here for the speaker one, 1, 2, 3, it is 3 lambda. For the speaker two, it is 1, 2, 2.5. Yeah, that makes sense to you. So the difference should be 3 lambda minus 2.5 lambda. It is 1.5 lambda. Yeah, that makes sense to you. Yeah, it is half lambda. Yeah, this is what we observe from this image. And in the yeah, the general rule for identify whether constructive or destructive interference occurs in the same for is the same for spherical waves as it is for waves traveling along a line. Actually, it's a similar thing. For the constructive interference occurs when the difference like a difference like a path length is a number, like the whole number, like a wavelength. And for the constructive interference occurs when the path length difference is like a whole number plus whole number like a wavelength plus half wavelength. That makes sense to you. It's just similar with the like a wave traveling along the line. Wave traveling along the delta D equal m lambda, m equal 0, 1, blah, blah, blah. And like delta D equal m plus half lambda, m equal 0, 1, 2, 3, yeah, blah, blah, blah. Yeah, this is just similar with like the constructive destructive interference occurs. It's the same for spherical waves as it is for waves traveling along the line. Yeah, does it make sense to you? Okay, let's talk about like the tactic box 60.1. Identify constructive and destructive interference. Actually, you can find this in the textbook. Yeah, and the first step, and identify the path length from each source to the point of interest. Compute the path length difference. Yeah. First step, you just compute the past tense difference. Then step two, like a find the wavelength. If it is not specified, if it is given you directly, yeah, you can just use it. Like then, if the path length difference is a whole number of wavelengths, like for example, lambda, 2 lambda, 3 lambda, blah blah blah. Crests are aligned with crests, and there is constructive interference. Yeah, and for the if the if the path length difference is a whole number of wavelengths plus a half wavelength. Yeah, this is a whole number of wavelengths, lambda, 2 lambda, 3 lambda, 4 lambda, like that. Plus, here is a plus a half wavelength. Yeah, like crests are aligned with stones, and there is destructive interference. Yeah, This is just how to identify constructive and destructive interference for spherical like a wave. Also for the string wave. That makes sense to you? Okay, let's view some quick check questions. Yeah, there are two in-phase source emit sound waves. Here is source one, here is source two. Those two in-phase source emit sound waves of equal wavelengths and intensity, which means the wavelength is the same thing and the amplitude is the same thing at the position of this dot. You can see, and the interference is constructive or destructive or somewhere between constructive and destructive, or not enough information to tell about the interference. Actually, for this question, we just need to calculate the path length difference. Am I right? Yeah. From source one, you can see here is lambda one. Here's 1 point lambda. Yeah, 1 point lambda R1. R1 equal 1.5 lambda, am I right? Equal and for R2 equal what? 1 lambda, 2 lambda, and 2.5 lambda, which means the delta lambda equal what? Delta lambda equal R2 minus R1 equal what? 2.5 lambda minus 1.5 lambda equal lambda, which means the distance is just lambda. So it's obvious. I'm right. The answer is obvious. It should be constructive. Does it make sense to you? Yeah. Yeah, the answer is A. And let's talk about an example. Yeah, 60.11. Like, is the sound loud or quiet? Yeah, two speakers are 3 meter apart. Yeah, there are two speaker one, speaker one, speaker one. Yeah, the distance between those two are 3 meter. And play identical tones of frequency 170 hertz. Sam stands directly in front of one speaker, like speaker one here. The distance is 4.0 meter. Is this a loud sport? The answer asks you, the question asks you, is this the sport Sam stand? Is this a loud sport or quiet sport? Assume that the speed sound in air is 340 meter per second. And let's try to analyze this question. Following step number like a tactics box 60.1, like this box here. Yeah, firstly, we need to find the distance. Am I right? Yeah, the distance R1, we know it is what? 4. R2, yeah, here is 3, here is 4. So we can use what equation? Do you remember that? Yeah, actually, here you can use Pythagorean theorem. Theorem. Yeah, I think you have already heard, like learned this, I think in high school at least. So if you forgot that and you just search it and recall this theorem, and those theorem which tell us R2 square equal R1 square equal this square 3 square. So which means R2 equal square root. Square root R1 square plus 3 square. Actually, it should be equal 5 meter. Yeah. And then we know the R1, R2, then we can know the path length difference, R1 minus R2, and determine whether it is of the form M lambda constructive interference loud sound or M plus half like a lambda destructive interference quite quiet sound. Yeah, this figure shows a visual overview of the situation, like showing the position of and path length from each speaker. Yeah, and yeah, Yeah, like we said, we use Pythagorean theory, and we can find R1, find R2. It is 5. This is 4. And then the path length difference is 4 minus 5. 5 minus 4, it is 1. And then we compute the wavelength because we know the here we know the velocity. It is free 340, and also we know the frequency. And then we can use it to decide the wavelength. Wavelength equal v divided f equal 2, which means the difference, the delta r equal what? It equal half lambda. And the impedance is half lambda. So this is a point of destructive interference. So here is a quiet spot. Sorry. Yeah, does it make sense to you? Yeah. Okay. Let's talk about this one. Yeah. Two speakers emit identical sinusoid waves, and there is two one. Sorry, let me put it in small. This is speaker one, this is speaker two, and those two speakers emit identical sinusoid waves. The speakers are placed 4 meter apart. This here the distance is 4 meter, and a listener moving along a line here, it move along a line, and in front of the two speakers finds loud. This is a loud spot, and this quiet spot. This is loud spot. Yeah, and the grid lines are spaced at 1 meter. What is the frequency of the sound from the two speakers? Yeah, actually here, like this, uh, there is a construct for the loud spot, for the two loud speed spot. Those are the constructing interference at each location, and the difference in path length to this location. For example, this one we set this, and the difference, distance to S1 is what? Is lambda 1 equal 3. 1, 2, 3, am I right? And this distance, lambda 2, is this is 3, this is 4. Yeah, we also can use the Pythagorean theorem. It is 5. So which means that the distance, the delta r equal what? Equal 5 divided 3. It is 2 meter. Am I right? And so, like percent of owning a single sport between two, you can see between those two two loud sport, there is only one quiet, and so which means this is lambda. Yeah, because this is the constructive interference location. So it should those two loud spot only have one. So which means those difference is just equal lambda. Am I right? Which means the lambda equal 2m. Yeah, here we know the lambda, and we know the speed for the is 340. So then velocity. So we know the f equal what? V divide lambda. Am I right? It is 340 equal divided 2. It is 170 hertz, which means here the frequency of sound from two speakers is 170 hertz. Does it make sense to you? Yeah. Only question, just let me know. Okay. Any questions? Let me know. Okay, let's talk about the beats. Yeah, what is a beat? Like the superposition of two waves with slightly different frequencies can create a wave whose amplitude shows a periodic variation. You can see here the yellow one and the purple one. Those two waves has slight difference, has slightly different frequencies. Like those two can create can create a wave, this wave, like whose amplitude shows like a periodic variation. You can see here is a periodic variation. The air hears a single tone that is modulated. The distinctive sound pattern is called beats. Yeah, usually if there are two waves with slight different frequency, actually your ear will now hear two different sounds. Your ear is just hear one sound with like a period with a fixed frequency. Yeah, those kind of like a situation from like those distinctive sound pattern is we call it beats. Yeah, does it make sense to you? Okay. And those this single tone, actually you the air our air hears this single tone. It is like modulated. Those two like signals has been like modulated as one like this. Does it make sense to you? Yeah. Okay. And the air oscillates against your like air drum at frequency this one like the air oscillator, yeah, because the superposition situation and F1 plus F2 is just like the air oscillates against your air drum. But the beat frequency is a difference between two frequencies that differ slightly. Yeah, this is the beat frequency, like the difference between two frequency. Yeah, like the frequency like oscillate determines the pitch and the frequency, the bit frequency determines the frequency of modulations. Yeah, I you can see here, this is just the like like the beat signal, like from loud to soft, from soft to loud. It's just a one beat. The amplitude is slowly modulated at frequency f like a frequency beat. Yeah, the medium oscillates rapidly at frequency. Here you can see the blue one. Yeah, the brown one is like a frequency beat, and the blue one is a frequency like oscillates. Yeah, okay, and the frequency oscillates determines the pitch, and the frequency beat determines the frequency of the modulation. Okay, let's talk about like let's talk about one some quick chat questions to like understand what we about the beats. Here are two speakers emit sounds of nearly equal frequency as shown. At a point between the two speakers, the sound varies from loud to soft. How much time elapses between two successive loud moments? You can see here those two uh like speakers, which means f beat, the beat frequency will equal what? F1 minus F2 like absolute, it will be 1 second. Yeah, which means the beat like frequency is just like the how long it is 1 hertz. Yeah, and how long? How long? It just a period. One divide f. It is 1 second. Am I right? So which is just like the how long exists between two successive loud movement. Yeah, it is just 1 second. Does it make sense to you? Yeah, because it just let you to calculate the beat, because here is just a 2 beat from loud to soft, from soft to loud. This 1 beat. Yeah, it's just like a one period. Like this is how long like between two successive loud moment last. Yeah, that makes sense to you. Yeah, we can calculate the beat frequency. Firstly, it is 1 hertz, and then calculate the period. It is 1/f, 1 second. Does it make sense to you? So we choose B. Okay, let's talk about the other one. You hear 2 beats per second when two sound sources, both at rest, placed simultaneously. The beats disappear if source 2 moves toward you while source 1 remains at rest. The frequency of source 1 is 500 Hz. The frequency of source 2 is what? Yeah, like you can see, if the source tube move forwards you, and then it will it will uh the the bits disappear, which means if the source tube move forwards you and the frequency after the source tube moves and the frequency is the same with the source one. So which means uh, uh, because the frequency of source it is 2 beats per second, which means the difference between those two is 2. Am I right? 2 hertz, which means otherwise it is 498 and otherwise it is 502, but it like source to moves toward you, which means according to the Doppler effect, the increase if the source to moves to you, which means the frequency will increase, and which means the first after the frequency increase it becomes 500, which means the original will be 498. Does it make sense to you? Yeah. Firstly, like the difference is 2. And then we will choose from B or D. And then the source move toward you, which means the frequency increase. After the frequency increase, it reached to 500. So which means the original is 498 according Doppler effect. Does that make sense to you? Okay, let's talk about the other one. Uh, yeah, the question. Let's talk about the example 16.12 detecting bats using beats. This is a biology example. Yeah, here the little brown bat is a common bat species in North America. It emits echolocation pulses at a frequency of 40 kilohertz. Actually, yeah, this is a common knowledge. Yeah, those kind of bits usually emit echolocation pulses at 40 around 40 kilohertz, well above the range of human hearing. To allow observers to hear these bats, the bat detector shown in figure combines the beat sounds wave at frequency F1 with a wave frequency F2 from a turnable oscillation. Yeah, this is a turnable oscillation. The resulting bit frequency is isolated with a filter. Yeah, the turnable oscillator generate a frequency a wave, a sound wave, and the frequency is F2, and the bat have the frequency F1, and then those two mix together, and then after that, and the result bit will is isolated with a filter, and then amplified sent to a loudspeaker. To what frequency? What frequency should the tunable oscillator to be set to produce an audible beat frequency of 3 kHz? Yeah, which means the difference should, yeah, because the f beats, the beat frequency should f1 divided f2 absolute, which means those this turnable oscillator. Otherwise, the frequency is 43 kilohertz. Otherwise, it is 37 kilohertz. That makes sense to you? Yeah. Let's talk about which one is this one. Yeah, the oscillator's frequency needs to be close to that of the bat's pulses, so that the resulting bit frequency is low enough for humans to hear. The bit frequency is this equation we already know. So the oscillator frequency and the bat frequency need to be differed by 3 kHz. An oscillator frequency of of either 37 kilohertz and all 43 kilohertz will work nicely. Yeah, we have already know that. Those two frequency are we have already analyzed this, and those two frequency are close to 40 kilohertz. A requirement to have a clear bit frequency. Yeah. So those two, 37 kilohertz and 43 kilohertz, also both work. Yeah, for this system. Yeah, does it make sense to you? Okay. Let's talk about those this example problem. A typical police radar sends out microwaves at 10.5 gigahertz. The unit combines the wave reflected from a car with the original signal and determines the bit frequency. The bit frequency is converted into a speed. If a car is moving at 20 meters per second toward the detector, what will the mirrored bit frequency? Okay, let's talk about this example. Do you have any idea of any ideas about how to calculate it? Yeah, actually, it's not difficult. You can see here, like the car, like velocity, car is 20 meter per second. Am I right? And here, like the beat frequency is converted, yeah, like as the car is moving at toward to the detector, 20 meter per second, which means like the Doppler, we need to calculate the Doppler shift frequency. Yeah, the Doppler shift frequency equal what? Yeah, actually we have already talked about in chapter 50. It is this is from shifted like a frequency equal to fs v no v, yeah, those is like the object frequency, and this is the like a like a speed sound speed wave speed like a sound wave speed, and this is like the car speed. So the shift frequency is two. Here is this is just the like a radar, like detector's frequency. Five uh yeah, this you need to like a 10.5 multiple 10 power 9. Yeah, and then multiple 20 meter divide 3 multiple 10 like power 8. Yeah, this is like a this is a light. Sorry, this is a light speed in like in air. Yeah, we just like this is approximately like a speed. So this is a radar. So this is radar signal. Yeah, so then we can calculate the bit frequency. Yeah, the bit frequency is just like a the like the shift frequency. Sorry. Yeah, it should be equal what? 100 hertz, 1400 hertz. Yeah, you can calculate it by yourself. Yeah, actually, yeah, this question is like the bit frequency is absolute value of the difference of the emitted frequency with the received frequency, which is the same as the shift in frequency on reflection. So yeah, this is the equation how to calculate the like shift in frequency, and this shift in frequency is just like a it's just the bit frequency. Yeah, we just this question let us to review the Doppler effect. Yeah, any question, just let me know. Okay. Yeah, this is what we learned for the chapter 16. And for chapter 16, we talk about superposition and the like a standing wave. And based on the standing wave, we talk about the how the speaking, how the hearing going, and what's the theory behind that. And also we talk about the interference for two different or more different wave sound wave or other waves will interfering will have the interference like a phenomenon with each other. So how they interfere with each other, and we talk about this, and yeah, you can like review all these things after this class. And okay, let's do a summary. Yeah. Firstly, let's review some general principles in the yeah, the displacement of a medium when more than one wave is present is the sum of the displacements due to each individual. Yeah, this is superposition. A different, more like a one, like two or more waves can if they met in one same position, and then the displacement will be the in this point will be the sum of the displacements due to each individual wave. Yeah, this is the principle of superposition, and also since because the superposition, like a then two or more waves into a single wave is called interference. And there are two different interference. Constructive interference like occurs when crests are aligned with crests and thorns with thorns. And the waves so tall tolls with tolls. And the waves are in phase. It occurs when the path length difference, like delta D, is a whole number of wavelengths. And the other interference is destructive interference occurs when crests are aligned with uh, song, and the waves are ordinal phase. It occurs when the path length difference delta D is a whole number of wavelengths plus half wavelengths. Yeah, this is what we talk about today and last week like that, and last class. Yeah, and we also talk about some important concepts like the first one is standing wave. And two identical traveling waves moving in opposite direction create a standing wave. The boundary conditions determine which standing wave frequencies and wavelengths are allowed. The allowed standing wave are models of system. Yeah, and this is a standing wave on a string has a node at each end. You can see here. There here is the possible nodes for the like a standing wave. And also for a tub, like sending sound wave in a tub can have different boundary condition: open, closed, or open, closed. For the open, and closed, they have the same equations to calculate the frequency and the wavelengths. Yeah, but the open closed, they have different equation. Yeah, the frequency will half according to compare with the open, closed situation. And also there are some applications. The first one is we talk about the beats. Yeah, beats it is like a low soft modulation of intensity, produced when two waves of slightly different frequency are superimposed. Yeah, here is the brown one is just like the frequency beats look like. Yeah, and the blue one is just the oscillator like frequency. And yeah, standing waves are multiples of fundamental frequency. The frequency of lowest model, it is standing waves. The fundamental frequency is the frequency of the lowest mode. The higher modes are the higher harmonics. Yeah, for sound, the fundamental frequency determines the perceived pitch. The higher harmonics determines the tone quality. Yeah, we have already talked about this. Our vocal cords create a range of harmonics. The mix of higher harmonics is changed by our vocal uh, 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 interact to create different vowel sounds. Yeah, this is what we learned in chapter 16. Yeah, just try to focus on how to what is superposition, how to calculate those two the frequency, the wavelength, how to decide the interference is constructive or disconstructive by calculate the distance, path length, the difference. And then for the standing waves and for different standing waves, we can calculate the wavelength and the frequency. And yeah, this is for different situation of standing wave and how to calculate it. And yeah, and for the beats, and you need to know how to calculate the frequency for the beat. And this is to to select different frequency, the difference of that these two slightly different frequencies. Yeah, this is what we learn in chapter 16. Yeah, if you have any question, just let me know. Yeah, because there are too many things here, but just focus on the not just focus pick mostly focus on the important ones. And then if you are interested in the other things, you can like review the textbook. And any question, just let me know. Okay, this is today's class, and we will have the class. We will have the exam tomorrow, and I will upload the exam questions in a PDF form in Blackboard, and it will be available at 8 a.m. tomorrow morning, and you can download it and write all the answers in in your notebook or in some paper, and then upload what you have what all the answers to the Blackboard. Does it make sense to you? Okay. Okay. Yeah, this is today's class. Yeah, and any question? Yeah, and I also have the office hour tomorrow. I will be in my office and from actually I will be in my office from 10 to 4 tomorrow. And I will be on Zoom from 11 to 12. Yeah. Uh, from 9 to 10. Yeah. If you have any question, just drop by or be on the Zoom meeting. Okay. See you. Bye.